Hi everyone. If you're not familiar with the Bluetooth Special Interest Group, by the way, we are the organisation behind Bluetooth technology. But just to be clear, because I know this sometimes causes confusion, we don't make Bluetooth products or components. We're actually a standards organisation, so our work concerns the large collection of technical specifications that define how Bluetooth works and how it must be used in different types of products, as well as the roadmap and general evolution of the technology. The overriding goal that we have as an organisation is to foster interoperability through standardisation, so you can buy your products from different manufacturers and they should all work together. So it's actually the manufacturers and kind of specialist software companies who implement Bluetooth stacks following our specifications. So that's who we are. Now, Bluetooth has come a long way in the 21 years since it was first released. Quite amazing. There's been a process of what I call continuous evolution, which a large number of experts from all sorts of companies have contributed to, and as a result we now have 3 different Bluetooth technologies to choose from. So shown on the left here, Bluetooth BR-EDR is the formal name of the original Bluetooth. So BR-EDR stands for Basic Rate Enhanced Data Rates, and it acts like a cable replacement technology, allowing data to be exchanged wirelessly between 2 connected devices only. Bluetooth Low Energy, or Bluetooth LE as it's also known, is newer. It was designed to be highly power efficient so that devices can be powered from small batteries that last years in some cases. It's also much more versatile though. So as well as supporting communication over connections between 2 devices, it also supports broadcasting of data so that one device can send data to an unlimited number of listening devices in a single transmission. And Bluetooth Low Energy is where most of the action is these days. And finally, we have the topic of my talk today, which is Bluetooth Mesh. So this technology was released a few years ago, and it completely changed ideas about what you can do with Bluetooth, because Bluetooth Mesh lets you create networks of tens of thousands of smart devices. It's designed for applications like smart buildings, which have all sorts of devices and systems, and exploits automation in many ways, often with the goal of becoming more energy efficient. So a Bluetooth stack is fairly modular. Architecturally, it consists of a host part and a controller part. The controller sits directly on top of the radio transmitter receiver hardware, and it handles all the low-level stuff. The host contains higher level protocols, and APIs are usually built on top of these higher layers. What you can see on screen now is the Bluetooth LE stack configuration that a smartphone has. It supports discovering and connecting to other Bluetooth Low Energy devices and then interacting with them. And these capabilities are provided by layers called GAP, GAT and AT, and you sometimes see these terms in APIs. So GAP is the generic access profile, GAT is the generic attribute profile, and AT is the attribute protocol, which is the main protocol used when connected devices talk to each other. Bluetooth Mesh uses the same Bluetooth Low Energy controller, but the host component contains completely different layers, collectively concerned with mesh networking. So since Bluetooth Mesh uses Bluetooth Low Energy for wireless communication low down in the stack, it therefore inherits many of the benefits of that technology. Now, smartphones do not have the Bluetooth Mesh stack shown here, but that doesn't mean you can't write smartphone applications for iOS or Android that work with the mesh network. All will be revealed. Okay, so what I want to do next is to introduce you to Bluetooth Mesh properly, starting with some of the most fundamental concepts. We'll start here with 3 important principles of multi-hop, multipath and multicast. So Bluetooth Mesh operates in an interesting way because communication between devices is not constrained by the range of the radio transmitter, because messages can hop from device to device to travel right across the network. This means that the area which can be covered by a Bluetooth mesh network can be very large. Bluetooth Low Energy version 4, which is the Bluetooth radio technology which Bluetooth mesh uses, has a point-to-point range of about 400 meters in ideal conditions. A Bluetooth mesh allows messages to take up to 127 hops. So, as you can imagine, a network can span a very large area, entire buildings, business campuses, and maybe even whole neighborhoods. Now, with a little thought when designing the network, messages take multiple paths through the network in parallel. This makes communication between devices reliable through redundancy in the network design. If one path is unavailable for some reason, the message will make it to its destination via one of the alternative paths. Almost all communication is multicast, so this means that you can control a very large group of devices all with a single tiny transmitted packet, and this makes for a very scalable wireless mesh network. So, devices talk to each other using messages, and devices contain a series of state values, each reflecting some aspect of the device and its current condition. Messages either report state values or they change them. State values feed into automation procedures, and changing a state value will change the condition of the device in some way. So messages are various types, and the state values they act upon are the basis by which a network and its devices are controlled. And Bluetooth Mesh defines an addressing scheme. All devices have a unique 16-bit unicast address. Messages get sent from a unicast source address, but usually the destination address is a group address, which refers to a set of more than one device. The mesh specification defines collections of specific state and message types, but broadly there are 4 classes of message. A status message reports on the value of a particular state, and it can be sent at any time by a device. A get message asks for a status message, which it receives in reply. Set messages change a particular state value in destination devices, but there are 2 types of set message. Acknowledged set messages generate a status message as a reply from every device that received the set message, whereas unacknowledged messages do not generate a reply. Now, perhaps counterintuitively, we only use acknowledged messages for one-to-one device interactions, such as when we're configuring a device. This is because using acknowledgements in multicast communication just doesn't scale. You can easily generate a storm and saturate the network, so most of the time we use unacknowledged messages only. Now, to make unacknowledged message communication reliable, each device is configured so that copies of messages get rapidly retransmitted a number of times in quick succession to get messages through. This is all about probabilities. If there's a 0.01% chance of message loss, for example, then sending that message 3 times results in the probability of all 3 messages failing to be received falling to 0.0000001%, very low probability. So that makes it very highly reliable. So Bluetooth Mesh uses what we call a publish and subscribe model of communication. I'm sure you've heard that term before, as it's quite common in message-oriented communication systems. Devices get told during configuration which destination addresses they should be interested in, and this is called subscribing. When a device sends a message, this is called publishing. The devices respond only to messages published to addresses that they have subscribed to. Others they may happen to hear are simply ignored. So when a device publishes a message to a group address, it doesn't know the addresses of the individual devices which will respond to it. And this is good because it means that if the set of devices which have subscribed to that address changes, for example when a new light is added in the hallway, this has no impact at all on the light switch, which continues to publish on-off messages to the hallway group address, and all of the devices subscribed to that group address will respond, including the new light. Now, once a device has been added to a network using a security procedure called provisioning, we call this a node. So nodes are made up of a collection of software components, and we call the combination of these parts the node composition. So as you can see, a node contains one or more things called elements. An element is an individually addressable part. So strictly speaking, messages get sent to and from elements rather than devices or nodes, though for convenience we often just say node. Elements themselves contain models. Now think of models as software components that give a node a set of tightly related capabilities, like the ability to be switched on or off, or to have a level of some sort changed. Associated with each model is a set of specific message types and states. So models are very much like classes in object-oriented programming. The mesh specification defines lots of different models. Perhaps the most important are the generics collection. The generic models are simple models representing some of the most fundamental things any type of device can do, like it being able to be switched on or off. Other model collections involve things like commercial lighting, which is way more complicated than you might imagine, sensors, time-based network procedures, and automation scenarios. Now models can be clients or servers, and here you can see the generic on-off client and generic on-off server models. And the difference between clients and servers is that servers contain state values, whereas clients do not. So here's an example of a fictitious Bluetooth mesh product with its node composition. It's a lighting strip with 3 LEDs, and they each need to be individually controllable. That was in the spec from the product management team. So the firmware in the product represents each LED as an individual element, each with its own unicast address. Each light can be switched on or off, and so the elements implement the generic on-off server model. They're also dimmable, and so this capability is provided by one of the lighting models, the light lightness server model. So that was a quick tour of some of the most fundamental concepts of Bluetooth mesh. But as a Bluetooth mesh smartphone developer, for reasons I'm going to explain soon, you also need to know about Bluetooth low energy connectable devices and the concepts that apply there, because this is the type of Bluetooth device that you have APIs for. So Bluetooth low energy connectable devices contain something called the attribute table. It's a table of data items which have values that relate to some aspect of the device, a bit like states in mesh devices. Procedures relating to the attribute table are covered by GATT, that's the generic attribute profile which I mentioned earlier on. And any actual communication between devices that concerns operations that act upon the attribute table take place using the attribute protocol. So hopefully those names make more sense now. But the attribute table is more than just a list, it's actually a hierarchy. The data items are more formally called characteristics, and they have a type and a value, and they live in groups called services. Services logically group related characteristics together and provide context for how they're used. And characteristics will sometimes have descriptors attached to them. This is optional. Descriptors provide additional information about the characteristic, kind of metadata, or they sometimes allow its behavior to be controlled in some way. So applications that work with Bluetooth low energy connectable devices generally have a similar flow. The first thing you need to do is to scan for devices in the environment and use filtering to pick out those devices that seem relevant to your application. So those devices are called peripherals, and they'll be doing something called advertising, which means broadcasting small packets of information so that they can be discovered. Now, the information in those advertising packets will give some indication of the type of device that it is and its capabilities, and this will form the basis of any filtering that you do. Now, typically you'll display a list of discovered devices to the user, have them select the one they want to connect to, and then you request a connection to the selected peripheral. And then you do something called service discovery to find out more about the device and to check that it's suitable for your application. Then you interact with the device, doing things like reading characteristic data values or writing to them, or enabling notifications, which will result in a stream of characteristic values being delivered to your application either on a timer or every time the characteristic value changes. Okay, so that's some theory. Let's have a look at the Bluetooth Low Energy APIs in Swift. So everything you'll need is in the core Bluetooth framework, and some key classes are here. CB Central Manager lets you do things like scan for advertising peripheral devices, and CB Peripheral of course represents one of those devices. There are also classes representing the GATT service, characteristic and descriptor constructs that I mentioned, and the delegate pattern, you'll find that is commonly used with both the central manager and the peripheral classes as well. I guess you see that a lot on iOS anyway. But what about Bluetooth Mesh? Well, I said right at the start that you don't have a mesh stack on an iOS device, therefore you can't really have native mesh APIs. But don't worry, because all is not lost, because one of the things that in principle any Bluetooth mesh node can do is to act as something we call a mesh proxy. What that means is that it supports both the Bluetooth Low Energy connectable device configuration of stack and the Bluetooth mesh stack, so you have both on one device. And smartphone applications can discover and connect to a mesh proxy node just like they can with any other Bluetooth Low Energy peripheral device, and then they can inject mesh messages into the network using characteristic write operations over that proxy connection. The application can also receive mesh messages which are delivered inside GATT notifications. So everything you know already about Bluetooth Low Energy programming for iOS applies. All you need to do that's new is to formulate your data values correctly. So if you've worked with Bluetooth Low Energy at all in the past, everything else should be already familiar. So here's some code by way of example. This just shows me using the central manager to check that Bluetooth is switched on, and then setting up a timer which will cancel scanning after a period of time, and then calling scan for peripherals on the central manager object to kick off scanning. Then the central manager's delegate, it's going to receive callbacks for each advertising packet. Because in this particular example I know I'm looking for devices that advertise with a particular device name, I use that in my filtering. You could obviously use something else. You can scan for devices that are advertising a specific service, which is important for mesh as well. You'll see more on that later on. Then what I do further on in that same callback function is add any selected device that I haven't seen before to an array. So I build up a list of the devices that are being discovered by the scanning process. Writing to a characteristic, which is what I need to do to send a mesh message into the network via a proxy node, only takes a few lines of code. So here I'm just calling write value on a CB peripheral object, and I'm supplying a value as a byte array and a CB characteristic object as the parameters. Okay, so let's bring it all together now. Part of the Bluetooth mesh system is a protocol called the Proxy protocol, and it's this protocol that's used by smartphone applications communicating via a proxy node. So overall, the architecture looks like this. The network includes at least one proxy node, and here we have a Swift application which is connected to it. Now the proxy has a GATT service called the mesh proxy service, and this contains two characteristics: mesh proxy data in and mesh proxy data out. So to send a message from your application into the network, you formulate a Proxy Pdu and write it to the mesh proxy data in characteristic. To receive mesh messages from the network, what you do is enable notifications on the mesh proxy data out characteristic, and the notification values that you receive contain mesh proxy PDUs, which themselves contain the mesh messages. So when sending messages via the proxy, again, the only sort of special issue really that you need to take care of is in formulating the value that you'll write to the mesh proxy data and characteristic. The value written must be structured as a mesh proxy PDU, and this acts as a wrapper for other types of mesh PDU, and of course you'll find full details in the mesh specification. But as you can see, there are three main sections at a high level. There's a segmentation and reassembly field that lets us split large proxy PDUs into a series of pieces. The type field indicates one of four mesh PDU types that the proxy PDU can contain, and usually you'll be sending network PDUs. Then we have the data field, which contains the mesh network PDU itself. If we look more closely at that, we'll see that the mesh PDU in the data field has three parts called network, transport and access, and these correspond to different layers in the mesh stack. You can see the kind of data these three PDU parts contain. So the source and destination address are in the network part. There's more segmentation and reassembly data for the mesh network PDU in the transport part, and the mesh message itself with its identifying opcode and its parameter values appear in the access part. Now, all mesh communication is secure, so there are some security requirements to be fulfilled when formulating PDUs as well. So the network part is obfuscated using an algorithm which involves the AES encryption algorithm. The transport part gets encrypted using a mesh network key, and that uses the authenticating AES CCM crypto algorithm. And then similarly, the access part of the PDU is encrypted also using AES CCM, but this time with a mesh encryption key called the application key. Now, both the network key and the application key are created when the network is established, and of course your application has to have copies of these keys to be able to work. Not surprisingly, to be able to do this stuff, you need a suitable crypto library to implement these particular features. In terms of code, there are only really three sort of special ingredients. You're going to be working with byte arrays, so uint8 will be your new friend. You'll need a crypto library. I've been using one I found on GitHub, an open source one, which has worked quite well for me. And you'll also need to do a bit of large integer arithmetic for one of the algorithms, and so a suitable library for that is also going to be needed. And again, you know, I found one on GitHub which seems pretty good, fit for purpose certainly. So here's some code. All I'm doing here is creating a byte array with a proxy PDU in it. Most of the detail is actually happening in some functions I'm calling from here. I'll tell you where you can find all of this code later on, by the way. I then write the PDU to the mesh proxy data and characteristic on the mesh proxy node that I'm connected to. And finally, increment a sequence number field, which is a field that all mesh PDUs have and which provides protection against replay attacks. And this is what a PDU looks like. So this is a screenshot actually taken from a Raspberry Pi that was acting as a dummy mesh proxy. So I wrote the code for this. I implemented the mesh proxy service, but it doesn't do anything with PDUs written to the data in characteristic apart from to decrypt it and then log its contents to the console. So I just wrote this for testing purposes. Now, I also wrote an application in Swift that lets me control the on-off state and color of the LEDs in 16 Bluetooth mesh nodes, which I'd like to show you in a video I prepared earlier now. So bear with me whilst I switch to the video. So here I'm just assembling my demo. I've got 16 of these developer devices. They're microcontrollers that have the Zephyr open source OS running on them. I wrote the code to implement the Bluetooth mesh models that they need, which is the generic on-off server model, and something called the light HSL model, which gives you color control. HSL, of course, is hue, saturation and lightness. Each of the devices subscribes to 3 addresses. They all subscribe to address which represents the whole collection of 16 nodes, and then each subscribes to an address for the column it's in and one for the row that it's in. I've got a separate device acting as a proxy at the bottom there, so my application scans for it and then connects to it, like so. And then my UI springs into life, and I can select destination addresses. You'll see that changing at the top of the screen there, and send different types of message. So I'm sending messages to the address C001 here, which I'm using for all devices. I've just changed it to C22, that's one column only, and I'm sending on-off messages to the selected device destination address. So you can see how subsets of the network are responding. This is publish and subscribe in action. Switching them all off there, and now I'm going to start playing with the HSL server model messages. So these let me control color, so they're all on now, but now I'm sending different message types again to the all device address to change the color of all of them to blue. What am I going to do now? I'm hesitating here, thinking, okay, selecting one of the rows, changing that row to red, and so on. So you can see how publish and subscribe works to give me control over subsets of the devices in the network, and how different message types allow me to control different aspects of the behavior of those devices, or different state values inside those devices. And that's the general principle, and all that communication is via the device at the bottom of the screen there, which is my proxy. Doesn't have to be a dedicated device, by the way. You can have any device act as your proxy. So all of the code for that demo application is available in one of our developer resources, including the code for the actual mesh nodes themselves, not just the Swift application. You'll also find code for a similar application for Android, and also actually using web Bluetooth, so you can write a web application that uses a browser rather than a smartphone application to exercise the same type of control. So if you want to know more and you want to find that resource in particular, where might you go for more information? Well, Bluetooth.com is of course the place to go. That's our website. We have a collection of self-paced self-study resources we call study guides. They each deal with different Bluetooth topics. Between them they cover a whole range of platforms. They all contain hands-on project work as well, so if you're like me and you learn best through doing stuff rather than just reading, you'll like our study guides. So the Mesh Proxy study guide that this talk relates to is there on the list, and it includes the full source of my demo app, as I said. We've also got all sorts of papers on all sorts of subjects, and they're often a really quick way to learn about a subject. They're not a substitute for the formal specifications, but they do make the learning curve a lot less steep. By the way, I haven't actually used this, but I'm aware that there's a company called Nordic Semiconductor. They have in fact created an open source library for iOS mesh applications, which is on GitHub, so that's probably worth taking a look at as well. Nordic Semiconductor have got lots of experience with Bluetooth. So that's it. Thank you so much for listening. Really appreciate you being here today. Hopefully we have some time for questions now, but if not, feel free to ping me a question over Twitter or via the help system we have at Bluetooth.com. Thank you once again.